Thank you, everybody, for coming to the third semester's installment of the AMS Colloquium. Very excited for our speaker today, Dr. Stefan Wild from Argonne National Labs. But as is the tradition now, I figure if you do it twice, it's a tradition, right? So now we will continue our tradition and have our AMS Colloquium correspondents, Izzy Aguiar and Jessica Daters, present on... Oh, I forgot to turn the music off. There we go. Present on some interesting mathematical stories from around the department and beyond. So, hand it over to Jessica and Izzy.
Hey everyone, I'm Jessica.
I'm Izzy.
As many of you might have gathered from just living, we are in the midst of a pretty contentious election season, and we're constantly being inundated with these statistics saying this person's winning or this person's winning, but it's kind of hard to know which statistics do you trust and where do they even come from.
Yeah, so Dr. Constantine actually found this great article from the New York Times where they did a poll in Florida and took all of the raw data and they analyzed it and found their results. And then they asked 4 different pollster groups to also analyze the data. So they're just giving them the raw data, it's all the same data. And interestingly, based on like a lot of the assumptions that were made that according to the New York Times are all totally valid assumptions, they got pretty vastly different results.
Yeah, so one of the pollsters found that Clinton would win by 4 points, and another found that Trump would win by 1 point. So this is a 5-point spread on the exact same data. So this is more than just a margin of error. This is a fundamental difference in assumptions. So Izzy and I always thought that they probably just took in the data and made a simple confidence interval, and boom, there you go. But there's actually a lot more that goes into it. So yeah.
One of the first things that they took into account was who's a likely voter. So in this poll, they're saying like, who are you going to vote for? And then they ask you, how likely are you to vote? And so they have to take into account that someone who says that they're going to vote for Clinton, but then also says that they're not likely to vote, they probably shouldn't take them into account. So one of the first assumptions was how they decided who was a likely voter. So some of the pollster groups just depended on this self-report, and some looked at voter history to see which ones that they could take into consideration.
Yeah, so then in addition to who's going to vote, they have to make sure that the data that they collected matches the population. So for example, all this data is from Florida. So if Florida is, say, 75% white people, but 85% of the survey respondents are white, then you have to somehow weight that so that the data or you're weighting the data so that it's consistent with the population.
Yeah, we want the demographics to match up. And so that's another assumption is where they're getting their matching demographic from. So some pollster groups looked at the census data to see like what the voter demographic breakdown was, and some looked at voter registration. And these are things from race to age to party affiliation, and then they try and weight their data accordingly to make it match this demographic. And that weighting is another assumption that they make, is like how they're going to weight it. So there's the traditional way, which they didn't go into, and then there's also one group did a model. They created a statistical model and used that to weight their data, which again they didn't go into. Yeah.
So the conclusion of the New York Times article was that it's best to weight or to average all of the polls to try to figure out what the actual mean is, because each of these is just another sample or data point. And so the best way to try to estimate the true mean is to get as much data as you can and kind of take the average of all of that.
It's also super interesting because as voters and as citizens, we are super influenced by what the polls say. So there are a lot of people out there who say like, oh, if Clinton has a 72% chance of winning, whatever that means, then I'm gonna have a clean conscience and vote for someone else or not vote at all. So we're super influenced by what these polls are, but not necessarily looking into how these polls are analyzed or collected, or if we can even trust them to begin with, because look how different 5 different groups can come up with different results from the same exact data.
Yeah, so more than that, we think it's just really, really important for us and for us to encourage our friends to be really critical thinkers during this election season, and to not just take the first statistic that you see or the first statistic that aligns with what you want to see, but to actually do some research and realize the different assumptions that go into coming up with these numbers.
So now we're going to move on to something a little bit more comfortable and exciting, which is our very own Dr. Harriman. We had the privilege and honor of sitting down with him and talking with him this past week and learning so many interesting things about him. So contrary to popular belief, Dr. Harriman did have a life before he came to Mines, but we're not going to concentrate on that because the scope of our presentation is his time at Mines.
So Dr. Harriman came to Mines in 1989. When it was a primarily commuter campus. So he said that it was completely dead at night. If you can imagine it being more dead than it is right now at night, that's how it was. It was also only about 5 or 6% women, and now we're pushing 30%. And he said that all of the students were pretty nerdy, but I don't know how much that has changed.
So we were asking Dr. Harriman what some of his favorite memories while he's been at Mines are. One of them that he remembered was working with all of the young students that come to our school. Specifically, he remembered Dylan Jones, who was 12 years old when he came to Mines, who, like Dr. Harriman, is a self-proclaimed pi fanatic.
So Dylan had, at the time, pi memorized to 500 digits, approximately. And we asked Dr. Harriman, how in the world do you memorize a number to 500 digits? And he said that there is a strategy where you memorize a story or a poem where each word in the story obviously has a certain number of letters, and that number of letters corresponds to a digit of pi. So there's actually a parody of Raven by Edgar Allan Poe that is all of the digits of pi to however many digits long the poem is. And the impressive thing is it actually reads well. So if you ever want to impress your friends, that's how you do it.
Another one of his favorite memories at being at Mines was working with Ryan Sayers. He was working individually with him on a research project when he passed away, and after he died, Dr. Harriman actually got to publish some of the work that they were doing together and work one-on-one with his family to set up all of these wonderful things we have now, like the lab and the scholarships and the runs. And he said that it was an honor to be able to turn such a sad experience into something positive and something beneficial for the math department and for his family.
So in addition to getting to work with all of the students, he has pretty much traveled the globe. So as most of you may know, he is in transitional retirement right now. So beginning in 2017, he'll be only teaching in the spring semesters, which will finish up in 2019. So I asked him what his plan was, and he said that he hopes to offer his skills to professors across the world, where he will offer to go and help them on projects in exchange for travel and accommodations.
Which is a super clever way of getting to travel for free. Another one of the things that he hopes to do is continue volunteer work with the African Institute for Mathematical Sciences. He had the pleasure of working with them in 2008. What it is he went and volunteered for a month teaching a course on dynamical systems and chaos. And he said it's basically like a 24-hour job of teaching and going to the social events, and if he's in his office at 3 in the morning, someone's bound to stop by and ask a question. They've expanded a lot since 2008, and there are a lot of new countries where they're based, and he hopes to go travel to those places and volunteer with them.
Pending approval from his wife.
Yeah.
So I think one of the biggest things we learned from getting to talk with Dr. Harriman is that being a professor is one of the best and most interesting and most rewarding jobs in the world. So congratulations to most of you, you picked the right job.
And it's nice to know that all of these exciting things that he's about to go do, despite all of these things, he still is going to miss some things at Mines.
Yeah, he says that he loves getting to have lunch with Dr. Martin every day. He's picked up playing racquetball with Dr. graffiti. He loves having students drop into his office and getting to collaborate with his peers.
He said that math can be a lonely business and that collaborating with his colleagues and with students makes it a lot easier.
So we are so lucky and fortunate to have had Dr. Harriman in our department for so many years and to have had his contagious enthusiasm to help shape our community that we have today.
So thanks for listening to our presentation, and
Math solve, folks!
Okay, let's thank Jessica and Izzy one more time. And now I will interview our speaker, Stefan Wild, from this beautiful beach location. So I introduce Dr. Stefan Wild from Argonne National Labs. We have a gift for you as our colloquium speaker. So thank you for joining us.
Is that part of the interview that I need to open it?
You're welcome to open it now and show extreme surprise and pleasure on your face, or not. That's fine. So, Stefan, thank you for visiting us at the AMS Colloquium. You're a computational mathematician at Argonne National Labs. You've been there since about 2008 as a postdoc. So how would you compare and contrast being a mathematician at the labs versus a university?
So probably before the last segment, I would have said that one of the things I have said at National Lab is there's more collaboration among the permanent research staff than in a typical academic environment. And that's partly because in an academic environment you have graduate students, and so often your main collaborators are your graduate students. And so since we don't have graduate students, we often collaborate with one another, I think, more than a typical university. From the last talk, it sounds like that happens here very much. The other thing is there's an explicit focus on multidisciplinary research, and so we see a lot more kind of cross-cutting activities from the math and computer science division that I'm in with other parts of the lab.
With other science disciplines and science problems.
Yeah.
Well, that's a great segue to my next question. So you work on methods for optimization. What are some of your favorite applications at Argonne that require optimization?
So some of I'll show a photo of the advanced photon source. We've got one of the largest hard X-ray sources in the world. Right at Argonne, researchers travel from all around the world to do experiments there, and they collect data. And effectively, every one of them wants to then solve an inverse problem based on that data. And they have such a diversity of problems. They're constantly changing because there's so many fields represented there. And it's really amazing the sort of wealth of problems that come through there. So I think that's a huge source of problems.
You're also very involved in SIAM, Society for Industrial and Applied Mathematics. This summer you were a plenary speaker at the annual meeting that was in Boston. So why is it important for you to be involved in SIAM, this professional organization?
Probably because it gives me a chance to collaborate, to find out about things going on in applied math and industrial math in general that I wouldn't otherwise have the foresight to go and find out about. So I very much enjoy going to meetings, for example, where you can walk into a random room and see some high quality presentation and find out a new class of problems that you wouldn't otherwise be exposed to. So I think that's part.
Breadth.
And then just the professional network of people involved. I think that's something very useful, but especially for early career people, they should seek to grow as much as possible.
Yeah, we met probably through SIAM.
Probably.
Yeah. I'm wearing my SIAM shirt, so I'm representing. One of my favorite factoids about you is that you have dual citizenship and a Swiss passport. Interesting fact about Stefan. So how did that come about? And this is my last question.
So I was born to Swiss parents. I have a U.S. passport as well because I was born on U.S. Soil. So I was
U.S. soil in Switzerland?
No, in the U.S. So I'm what you would call an anchor baby, but from Western Europe. So maybe not the way that term is usually applied. And so yeah, by Switzerland's by birth. The more interesting fact is that, as I was saying to someone earlier, Switzerland requires military service of all males. And so to keep your citizenship as a male, then you, of a certain age, you need to go do basic training, and the U.S. doesn't like their citizens going and doing basic training in foreign militaries. And so I worked in high school, effectively, and right after high school I worked in the civil service on a farm in the French part of Switzerland in order to sort of not do military things, but retain my citizenship that way.
Cool. Mathematician and a farmer.
Yep, you got it.
And I forgot to mention, you also did your bachelor's and master's up the road at Boulder, right? In applied math.
Yep.
So somewhat local. Okay, well, with that, Stefan will give his talk. And I will go to his talk. And he's going to tell us about black box optimization. So please welcome Stefan Wild from Argonne National Lab.
So thanks again, Paul, for the introduction. So I think I'm a little bit more than somewhat local. I went to high school in Evergreen, just a few exits up the road, actually, and then was an undergrad in Boulder, and so I drove through Golden often during those first years, at least where my parents still lived in Evergreen. So it's, in case someone hasn't told you today, you should really enjoy the fact that you live in Colorado or get to work in Colorado. Yeah, anyway, it's a pleasure to be back. Thanks for the introduction. This is joint work with a number of people that are at Argonne. Many of them came through student programs for graduate students that we have at Argonne. Those who didn't often did a postdoc at Argonne before they stayed on at Argonne as staff. And so that's going to be a sales pitch at the very end for many of the people in the room. Cool. So I won't even do all of this. I will just go straight and show you how this is not aligning the way that it should be. All right, so somebody with a mat needs to go.
There you go. You have to go view and enter full screen. Very bottom. Right there. Give it a good click. There we go.
All right, excellent. So it's not quite full screen, but good enough. So this is Argonne, or was Argonne a couple of years ago. From above, I say not quite because the building that I've been in the last 5 years is sitting over here in the forest. The key thing to say about this is each one of these buildings represents something like an academic department or college at a university. So we have a chemical engineering department, high energy physics department, a physics division, math and computer science division is the one that I'm in. There's energy systems, material science, the advanced photon sources, this enormous ring that you see over there. They have their own set of tricycles that you use to travel from one part of the ring to another. You have to take a special training course for. Cafeteria is sitting over here. Anyway, so a large research campus. Unlike some of the other national labs that you may be familiar with, we are an open science laboratory, so we're not associated with the weapons program. Our purpose is to advance science for the sake of advancing science's case, especially in areas of interest to the U.S. Department of Energy, who's our chief sponsor. As a result, we look much more like an academic setting. Here we've got people from all countries and backgrounds. The majority of research staff members are not U.S. citizens, things like this. It tends to be a very dynamic environment, and so I've liked it so far. So I'm going to talk about simulation-based optimization and derivative-free optimization, and this is the overview in one slide while I still have everyone. So we're trying to minimize some scalar function little f as a function of the things that we can control. These are the parameters x. They're going to be an n-dimensional vector, think of that. And what makes it simulation-based optimization is that this function f that I want to minimize, the objective function, is really some mapping f over here of both x and some output of some simulation. That's the s of x. So throughout the talk, s of x is some generic simulation. Typically I'm going to be talking about deterministic simulations. So the statisticians may have to put an expected value or something over here, potentially. There may be constraints that I want to satisfy. I want the x to also satisfy some constraints. That may also depend on the simulation output over here, whether they're inequalities or equalities. So simulation-based optimization just means there's a simulation in the picture. And for our purposes, the s is going to be red. And the s is going to be red because the s is going to be the expensive part. So all of my effort is really going to be coming into this s of x over here. And this shows up in a variety of ways. Maybe you're doing parameter estimation for a particular class of simulations or model calibration, design optimization on top of a simulation output, so on and so forth. So this S is going to be the simulation mapping over here. And a challenge for optimization that we'll go into some detail in a few minutes is that the derivatives with respect to these parameters x of the simulation output are often going to be unavailable. I may know what this capital F mapping is and what its derivatives are with respect to its inputs, but I don't know what the derivatives of S with respect to X are. Furthermore, a single evaluation of this simulation over here could be very expensive. And this fundamentally changes the way in which we think about optimization algorithms for solving these particular problems. Generally, in optimization, what we're worried about is how to minimize the number of linear algebra operations that are needed to compute our next X that we're going to evaluate the objective and constraints at. In simulation-based optimization, that linear algebra for that decision process is trivial relative to the expense to evaluate this S of x. And so that's going to lead to slightly different algorithms than we would see in classical optimization. These things arise everywhere. Throughout the lab, we've worked with people on medical and bio things. The simulation need not be numerical. It can be an actual physical experiment. So somebody's doing synthesis in the lab. They get some noisy observation, and based on that, they're going to go change the inputs to the experiment and then loop around. Over here, groundwater remediation is something that we worked on, even sort of tuning the magnets for the APS. We'll talk about it a little bit at the end. I'm going until 10 till. Yeah, right?
Yep.
Excellent. Okay.
And you've got some wiggle room too. So
I will try not to take wiggle room because my voice won't make it. So why is this a problem that we see frequently at Argonne? It's really because of computing. Because now most of you in this phone have some multi-core computer sitting in your pocket. And it's everywhere. Argonne has a rich history in computing. So in 1953, this is what our computer looked like over here, completely based on vacuum tubes. The computer that's still upstairs for me was installed in 2012, so in my building, that's a Blue Gene Q. It's got almost 1 million cores over here. So this is taking up some, just for reference, so this rack is about 6 feet tall right here. And of course, the fastest machine as of June of this year is a Chinese machine over here, and what you can see is that you can multiply by a factor 10 the number of cores, and that's how it's growing. Okay, so this is a reason why people are caring about, well, a reason why people care about simulation-based optimization is because they're worrying more and more about sort of high-fidelity simulation. How do we get more and more realistic simulation of physical processes and things like this? And then as the computer technology every time increases by another factor 10 or something, they start to ask other ways that they can use the machine for design purposes, for example, or to solve inverse problems. Okay? The problem is that these higher level decision problems of optimization, design, decision control, operation, uncertainty quantification, they're often an afterthought to the actual simulation. So a lot of the work that gets done in a typical, for the people working on PDs, for example, is on that forward problem. How do I make my simulation output as accurate as possible? And as a result, you end up writing simulation code that it's very hard to then take the derivatives with respect to those decision parameters, those x's. One particular way to do that is called algorithmic, or it used to be called automatic, but it's not so automatic, so they changed it to algorithmic differentiation. This is a way to generate sort of source code alongside the simulation source code for the actual derivative calculations. But if you if you do this as an afterthought, then there's lots of obstacles over here. Similarly, if you're working with industry over here where they have some proprietary code, you can't take a derivative of an executable only code. So there's some black box deep inside that simulation process over here, so you can't do the AD. So these are reasons why derivatives aren't there. Finite differences, of course, we know that's one way to get a numerical derivative. That's different from this algorithmic derivative. These numerical derivatives, they of course depend on the number of variables in the x that you have. So there's on the order of n function evaluations that you would need in the simplest case at every iteration to get a derivative. We want to do much, much better than this. Okay, so that's the general thing. We have computing. So what I mean by derivative-free optimization is simply that some, maybe all of the derivatives, the partial derivatives with respect to x of this mapping S of x are unavailable for purposes of optimization. That's what I'm going to call derivative-free optimization. That's different than non-smooth optimization, where those derivatives may not exist because you have the absolute value function or piecewise maxes, things like this, and so kinks, things like that. Yeah. So I am going to fundamentally assume in a few slides that mapping, that S of x, is a smooth function of the x's. All right, and so the challenge, of course, is that optimization is tightly coupled with derivatives. So if you look at what the optimality conditions are, what does it mean for x star? What are the first order necessary conditions for x star to be a minimizer of some quality constraint problem? It's that the derivative of my objective function f at x star and some linear combination of the constraints over here vanishes at this x star, and that I'm feasible as well over here. So you see the derivatives of the function, the derivatives of the constraint showing up exactly there. So if you don't have that, you may not even be able to recognize optimality. So this is the challenge. You don't know exactly where to stop, because typical measures for when to stop are the norm of the gradient in the unconstrained case, or projected gradient in the constrained case. You have problems with feasibility. I don't know which direction to go in order to satisfy my constraints, if I don't have a constraint derivative, maybe. I don't know which direction the objective function goes down, which would be the negative gradient if I had that derivative, so on and so forth. All right, so this is the problem. And so I'm going to go and skip this motivation and go jump right to black box optimization. So one of the things that we have at Argonne, since we do a lot of problems for the Department of Energy, is we have a large vehicle technology center. And so we get things like early Tesla prototypes 10 years ago and whatnot that get put basically through a large video game. So you see a man sitting over here. You see a computer screen over here that's showing him maybe the EPA's city drive cycle or something like this, so effectively the game that he needs to actually do. A whole bunch of sensors coming off of the vehicle to measure things. There's fans that typically get set over here for combustion engines because there's no wind or something like this. They worry about the engine overheating if it's just on rollers. So there's someone actually doing this video game process. And the idea is, how do you optimize the controllers in this car? How do you optimize the design of the car? Anything from the shape to the actual engines being used, for example, or the individual components being used, subject to sort of the uncertainty with the human driving through a particular drive cycle. Now, in the limit, I bring up this because then you get what we had with Volkswagen and the TDIs, right? So if someone is given an optimization problem which says, go make me a car that is as fuel efficient as possible and passes the test, someone can probably satisfy the constraint of passing the test. And then, if not test and you do the lookup, then do something else. And then you get what we have now. I can say that since my wife owns a TDI. And we get a new car soon. Okay. So this is what black box optimization is. This is a special case of derivative-free optimization in that the function that I'm trying to minimize, this f, is exactly the scalar simulation output. Okay, so my simulation returns one number. That's the number in this case that I'm trying to minimize. And then my only input-output relationship between my optimization algorithm and this simulation is the optimization algorithm passes it in x and gets back some f of x. So the only knowledge that it has about that f of x, truly the only knowledge it has, is from sampling. That's what black box means. So think of this as truly an experiment. You get a single number out from doing an experiment. Okay. And so this black box is going to be both a good thing and a bad thing throughout the case. It's a good thing because for the purposes of solving an optimization problem, the easiest possible interaction with your simulation and an optimization is if you just write a function that does this, right? Someone gives you an x, you give it an f of x, so on and so forth. It requires no additional output derivatives or vectors of output or uncertainties or things like this. All right, and black boxes actually exist, so I don't want to have you walk away from the second half of the talk, where I'm going to try to throw away everything you know about black box optimization and say that black boxes don't exist. So one example I think that I like of black boxes is how do we get a particular computer code to run as fast as possible on the new supercomputer. So often you do this if you know the Atlas, sort of the Tune BLAS libraries for linear algebra operations. That's exactly what we're doing. We're looking at a linear algebra kernel on two different machines, and then there are different ways that we can rearrange the loops in those different linear algebra operations to get the same code over here. The code that is best on one machine is very poor when you measure it on another machine. So here are the sort of best solutions for these two different machines. You can't just optimize for one machine, walk to another machine, and expect that it's going to perform well. So this is a black box optimization problem because there's an experiment that's run. You go do some code transformation, so you do some source-to-source transformation, you recompile the code, you run it on that actual machine, maybe some number of times because of variability, and then you get back your output. That's the black box over here that I'm trying to minimize. So black boxes exist. What are the type of algorithms that people use over here? So there are stochastic algorithms. Random search is the easiest one to think about. I've got to manage my time already. I'm not going to talk too much about stochastic methods for these. These have a rich history, and especially sort of you see this gap over here at Cornell in the 50s. People were looking at these things, and then there's a large gap. But recently, these have come back into favor, especially in the advent of machine learning and everything is deep learning and so on and so forth. There are also stochastic heuristics, so these are anything that follow under some nature-inspired category, genetic algorithms, evolutionary. That's absolutely not what I'm going to talk about in the course of this talk. And part of the reason is that these are typically global optimization algorithms. They do some type of global search, and that's going to be very expensive. They're going to do some dense sampling in the search space, and that's exactly what we're not going to do. We're going to be focused on local optimization, which means you give me an engineering starting point, let's say, that you want to improve upon, and I'm going to find a local solution as quickly as possible, hopefully a good quality local solution. All right, so we're not going to talk about those. So now that I'm in the setting of local optimization, deterministic optimization, we get to the class of direct search methods. So one class of direct search methods are pattern search and its variants, and these are very easy to describe. So the easiest one will be something like compass search in 2 dimensions. Over here, x1 and x2. I'm sitting at a particular point in space. I go some distance to the east, to the north, to the west, and to the south. I evaluate the function, and I ask myself, did I do better off than at the point that I was sitting at? So yes or no, is f of x at these 4 points over here that I've shown better than the current point that I'm sitting at? And maybe if the answer is yes, I'm going to move to maybe the best point, or move to the first point for which this returns yes. I repeat the same thing, and these methods have devices for growing and shrinking, that sort of stencil that you can imagine laying over these things. And even if the function is nonlinear, despite the fact that I'm just looking at coordinate directions in this special case, over here, these methods you can show will converge to the solution. You can even show that when derivatives don't exist, you just have a continuous function, but maybe you have things like absolute value, that these methods will also find actually a local solution. What about nil-intermediate, the simplex method? Instead of looking at these sort of stencils, these patterns, it's going to be looking at simplices in 2 dimensions. A simplex is just a triangle. So it's going to be doing an evaluation at some point, and then the points on the vertices of a simplex. There's 3 total points, 3 total vertices in 2 dimensions, and it's going to ask itself, what are the ordering of these points of the function values on these vertices? Depending on the ordering, it's going to do things like reflection, where it's going to take the worst point, remove it, reflect about the other face. Or expansion and contraction. So it has these similar operations to growing and shrinking the patterns over here, but it's just operating with triangles in 2 dimensions or simplices in higher dimensions. The key thing is that these are working on indicator-like functions. It's yes or no, am I better off than at the point that I was at? Or what is the ordering of the function values at these particular points? There's no notion of the magnitude of the function values at these particular points. So that if the ordering is the same over here, but this one was 1 billion times larger than these were, there's no sort of knowledge or capture in the methods, at least as I've written them. And so that is what's going to be filled. So that's sort of what's missing in this case, where you want to do as much as you can with this very little information that you have, just the sampling information. What can you do? So now I've introduced a 3rd dimension. The 3rd dimension is just the output of the simulation output. So here's the first parameter, here's the second one. The O's are what was missing before. And so if I do some sampling over here in this 2-dimensional space, and I see some O's, and I know that my function f is smooth, then I might use these actual O magnitudes to infer something about the behavior that's going on over here. And then maybe in the course of an optimization algorithm, the information might grow richer and richer, and I can use this information for the purposes of optimization. That's the generic thing behind a model-based method for local optimization. We're forming some local method. I'll tell you what local means here in a second. We're going to minimize that particular model within this local neighborhood, and then based off of how correct or incorrect our model was at that newly evaluated point, I'm going to grow or shrink my region. I'm going to move to my next point, so on and so forth. So what it's using is it's using smoothness, and now it also needs to store the magnitudes of the function values that I've sampled. That's what I'm doing. So that's why these things perform well. So this is called a trust region algorithm, or a model-based trust region algorithm. They need not be derivative-free. The ones that we talk will. The basic idea is I've got some quadratic. It's got some constant term. It's got some first-order term, a gradient, and it's maybe got some second-order term over here. I'm going to take my expensive problem and replace it by a cheaper problem. So rather than minimizing this expensive function f over all of our n, I'm minimizing a quadratic over some ball. And this is a problem that we can actually solve in optimization very well. Okay? So this ball is just going to be called the trust region. It's going to be parameterized by the point that I'm sitting at, the xk, and some radius, this delta k. It's going to be called the trust region because that's the region within which I'm going to trust my model to approximate the function, or more accurately, to tell me in which directions there are decrease. Okay? The updates are based off of, this is a very important device. It's the ratio between the actual reduction, so by how much did I decrease the function at that new point x plus, relative to how much I predicted the function would decrease over here. This is the actual reduction over the predicted reduction. And this is, again, the measure of quality that I'm using to tell me about whether I should be moving to my point, growing and shrinking my neighborhood. Okay. The key thing is, I don't actually need my local model to approximate my function completely in this ball. Again, it needs to be telling me which way is downhill. So if I get much better, more decrease than I predicted, I'm okay with this. That's the sort of greedy approach of this particular algorithm. It's only in the case when I'm not seeing large decreases that I have to be worried about this approximation quality. Okay. And the cartoon is exactly that. So again, I've got some function whose contours are here, but I don't know that function except for where I've sampled. I've got some local model, those are the shaded in contours. My local region is that region bounded by the red, and I'm going to move to the cool shaded regions in that space. That's a trust region algorithm. I do these evaluations. If maybe I'm seeing good progress, I'm going to grow that region. I can shrink the region, so on and so forth. And then follow this curved path to the solution. And you'll forgive me, I caught a little bit of a cold, stuck in a hotel room a couple nights ago, so I'm going to try to take care of my voice. If you have questions, by all means, interrupt. Okay, so model building, in the case of derivative-based optimization, you just take the gradient and the Hessian and you throw them in, or some approximation. How are we going to do it? We're not going to do finite differences at my particular point. We're going to do scattered data interpolation. So for quadratics, come up with some basis, and that's first order terms and second order terms, and coming up with a model just means solving a linear system, where I've got the function values on the right-hand side, some basis matrix over here, evaluated at the points in space, the x's, and I come up with the coefficients. And then you get different optimization methods depending on what kind of basis you use here and what it means to quote unquote solve this system. If you have exactly the right number of points for quadratics, roughly n squared over 2, and they satisfy geometric conditions that we'll talk about next, then you're sort of in the full quadratic case, the perfect case. There's a unique quadratic that goes through those data points for any of the function values that you could have on the right-hand side. If you have too few points or they don't satisfy these geometric conditions, then you could do things like minimize the least change from the previous iteration, second order information, or find the flattest quadratic that goes through the data. Or if you have too many points, then you can do regression, which the statisticians know much better than I. Okay, so I like to talk about this real fast. So again, why are our data scattered? Why are we not choosing the locations of these particular points? It's because we like to use the history of points that we've visited in the course of the optimization. Right? We want to be as greedy as possible, so we want every point to sort of be making us progress towards the solution rather than sort of be optimally spaced from a geometry point of view. So that's why we have to worry about scattered data interpolation. Everyone learns in numerical analysis 101 that if I'm living in 1D, if n equals 1, then if you give me distinct points, as long as the degree of the polynomial is right, then I can find a unique polynomial that passes through any of those function values. That's not true in anything but the first dimension. Okay? So in the second dimension, you get something like this. The magic number of points is 6 for a quadratic of 2 variables. If I have 5 black x's over here, the 6th point can't lie on these blue lines. Okay? And the geometric argument is that there exists a quadratic that disappears over here, and so I need to have something away from those things, otherwise I'm in the 0 level set for some quadratic, and therefore I couldn't get a unique quadratic. Okay, so there's a cool interpolation problem that's going on in the back end of this. And of course, because I live in a computer, I don't just have to worry about being on the line, I have to be worried about being close to the line, where close depends on the basis. And that's what the contours are showing here. That's a nice representation. If I have constraints, so suppose I have to stay in the yellow region, it's going to be more complicated. Because if I can't violate these constraints, I can't get information over here, I'm going to potentially have to do more evaluations in order to get some nice quadratic. Okay, so there's some cool numerical analysis problems. At the end of the day, you can show some some characteristics about your particular models. You can show that they satisfy Taylor-like error bounds. You can show that the quadratic differs from the function by some term of order delta squared for all the points in that ball of delta, radius delta. And you can show that the derivative, assuming it exists for that function, remember we don't have access to that derivative, but we're assuming it's smooth and so that derivative exists, goes down like something delta. So this is exactly the Taylor kind of result that you would expect, but you can show it just based on function evaluations, and that the data satisfies sort of nice conditions for those interpolation matrices. Lots of people have written methods over here. People in the room, like Peter Graff and Steve Billups, they've been looking at regression models. All of that fits exactly in this particular framework. It's a local trust region-based method, and they just have a different form of model, and that leads to a slightly different algorithm. Okay. But what we really want to talk about for the last 8 minutes, assuming my voice holds up, is exploiting structure. So moving beyond the black box in 8 minutes. Okay. All that this means is that my function f, this mapping over here, sorry, capital F, is not the identity mapping. I have some function of the simulation output, and that function is not the identity mapping. Now what do I want to do? Okay, so an example is that I'm trying to calibrate my simulation output to data. I've got some data points di over here, maybe some theta i's or ti's or whatever that I evaluate my simulation at, and I'm looking at something like the nonlinear least squares. That's what that first problem is. So now I get a vector of output for that evaluation. I get s at each of those sites, at each of those i's, and I know that my objective function depends on the residual squared, or the sum of the residual squares. That's what it means for capital F to be something other than the identity. I could have some composite non-smooth stuff. Again, I have a smooth function s of x over here that gives me a vector of smooth output, and then I'm taking some non-smooth function, maybe the one norm, because I'm trying to do some compressive sensing or something like that on the outside over here, and that's the function I'm trying to minimize, or some combination of terms over here. It could be that I have some decision parameters that enter into the simulation. Let's call those xj's, and I have other ones xi's that don't enter into the simulation. So these are all cases in which we know something about that function capital F over here that we're going to now exploit. So that's the key idea. Algebraic knowledge about that mapping F over here, we're going to exploit that in the same setting that I just talked about in order to do better than we would if we just worked with the one number, which is the scalar output over here. Okay. So again, I'm going to assume that each of these outputs, now there's these vectors of outputs from the simulation, that these are smooth, that their derivatives exist, but they're not available. And then now I'm going to build one of these local models for the purposes of optimization for each one of the outputs. Okay? So each one of these simulation outputs now has its own, let's say, quadratic model with its own first order and second order terms over here, and then they satisfy some approximation bound like this. This is an easy thing to do as long as the points that you evaluate these residuals at are consistent, are the same across all of these outputs. Why? Because the basis matrix is the exact same as in the one output case. It's just that now I've got one set of coefficients for each of the outputs, and I've got a right-hand side, the function values, the residual values for each of those. So this is just the same linear solve, just with multiple right-hand sides. Easy. And therefore, anything that I say about the first residual's quality, assuming the same assumptions for the other residuals, I can guarantee quality for the other ones. So how does this look like for the case of nonlinear least squares? Again, now I'm trying to minimize some function f, which has p outputs. These residuals are 1 through rp. I'm going to come up with a model for each one of them. So I is going to go from 1 to p, a first order term, a second order term. And all that I'm going to now do is look at the derivative of this function f, the objective function, see that its derivative depends on the residual derivatives, which I don't have. That's why they're red. That's what depends on the simulation. But a particular linear combination of them. And I know the linear combination. This is zero order information about the residual vector. Okay? So I have the RIs. I know that they involve in the sum. This is the unknown. So take the unknown, do this approximation over here. That's what I'm going to be using. Same thing with the second order information. Second order information, of course, you see now we're thinking Gauss-Newton, things like this. I see that the first term that I get is just the outer product of these residual gradients over here. Do that same sort of approximation. But again, I know a lot about the structure. I know that the first order information of the residuals are contributing to the second order information of the function I'm trying to minimize. And that's the key value. That's what's going to make the approximation quality that much better, and that's why it's going to work in practice. So once I have these approximate derivatives over here, then I can choose whatever method I want to solve these type of problems over here. The key thing is I'm going to keep this device that I get from the trust region purposes, which means that I don't just want to do approximation everywhere, I want to be predicting decrease. And so I need to only worry about my approximation quality when I'm not seeing decrease in this merit function that I'm going to build. All right, so we solve lots of problems with this. This is the main type of problem that we typically see, are these type of calibration problems where people are just looking for the MLE type things for the statisticians. You could do a similar thing under the Bayesian setting. You can imagine where now I've got the simulation coming up, and I'd love to talk to people about that. If we look at a method that doesn't take advantage of that least square structure, like the Nelder-Mead method over here, that's the method that these physicists were using beforehand. They weren't getting the solution quality that they were desiring. In sort of 2.5 days, that's when the computer time cut out, they were kicked out. But as long as they take advantage of this structure, then they were actually solving their particular problem. Okay, so you get much better quality, much faster, by building many of these models, one for each of the outputs. The cost is more linear algebraic operations. Now you have to store terms for each of these models, so you have to build each of these models, but again, under our assumption, that's negligible relative to the cost of that expensive simulation output evaluation. Okay, non-smooth optimization, just a quick overview over here. Suppose now that my function f, instead of depending smoothly on these simulation outputs over here, suppose I have something like a one norm sitting out there, or that I've got sort of these min-max type problems over here where I've got these piecewise components. So depending on what region of X I am, it's going to pick a different TI to be active for the particular objective. And that's what's especially interested in these particle accelerator type things. The first problem that walked into our door along these lines was exactly for regulatory reasons. Basically, someone was trying to clean up a groundwater site, and the penalty that they had to pay the regulator was proportional to the amount of contaminant that left each of the contaminant regions over here. So the flux across these regions over here. And so that's exactly what they wanted to minimize, the cost that they would have to pay under various remediation strategies, various pumping strategies for the wells that were on site. So again, the key thing is that we have some non-smooth function h, but that we know what that non-smooth function is. We have a smooth function, which is the simulation output, but we don't know it's not algebraically available. And so we're going to do the same thing as we did before. If I look at now, because we're in the non-smooth optimization setting, the subdifferential, I see that the subdifferential depends on some things that we know through zero order information, and some things that we don't know, the gradients of these simulation outputs. So I'm going to walk through the same type of model-based approach for the unknowns over here, so that I know, after I do my evaluation, am I at a particular kink or not? Are the SIs, for example, equal to 0? That's when I could be at a kink in this sort of landscape over here. And so then, now I'm going to be building approximations of the subdifferential based on that information. All right, so we'll fly it there. It doesn't exist. Real problems. The last thing that you can do is now for constraints. And this is the sort of second to last slide that I'll show then. So what do you do about constraints? The typical way that an engineer worries about constraints is they give it to a genetic algorithm through a penalty function. They take their objective plus some constant times the constraint violation. Okay, so that's what I mean by penalty. And then you just treat that as a black box problem. The problem with those methods is as soon as you do that, you can't disentangle optimality, what the objective function is telling you, from feasibility, because you've collapsed them together into one. And so if you look at sort of the merit functions that tell you about optimality, that's exactly what you see. That's this magenta lines thing over here. If you just give that penalized version to a black box problem, it's going to solve a related problem, but it's not going to know about feasibility. It's going to be slightly infeasible, in fact, in the case of augmented Lagrangian methods, and so it's never going to actually converge. So the first thing that you can do is just separate out the constraints from the objective function and build maybe two black boxes. One that's the simulation output that tells you about the objective function. One that's a simulation output that tells you about the constraint satisfaction, or the constraint violation. And that's, if you put this in this model-based structure, that's the sort of black line over here. Now you can disentangle feasibility from optimality, so you will actually solve your problem. It'll just take you a while. What if, on the other hand, the constraints are algebraically available, but the function, the objective function, is a black box? So the simulation doesn't depend on the constraints. If you take advantage of the derivatives from the constraints and do this black box thing now just on the objective function, then you get the red line, faster convergence. And if you realize that actually you have derivatives of everything, you can do AD through the simulation, then you get the blue. So this is exactly the price that you pay for not having derivatives of the problem. If you actually have derivatives and don't use them, and give it to some genetic algorithm or black box solver, good one, let's say, this is what you look like. If you disentangle feasibility from optimality, you end up over here. If you take advantage of some derivatives, you'll do better. And if you realize that you have all the derivatives, then in this particular problem, you can just solve the problem. Okay, so that figure is one thing I'd like you to take home, and I'll conclude. Okay, so the key thing is that for people that have been just worried about black box optimization and using some of these heuristics for convenience, they don't think about the real problems that they actually want to solve, because they're far too expensive. These heuristics require far too many function evaluations, so they're not thinking about the optimization problems or the UQ problems that they're actually interested in. For many problems, there is a black box involved. Someone wrote a legacy code in some physicist's lab 20 years ago, and that code stays with you throughout the process. That's just a reality that you're not going to be able to get around for a variety of reasons. But the idea is to disentangle, to follow the algebraic information that you have as deep as possible to expose that particular black box. And then you can solve the problem faster and better. Okay, so that's exactly what this says. There's a web page. Again, in my minus 2 minutes, I will say that there are awesome opportunities for especially graduate students at Argonne. The deadline tends to be in January of every year. Please send me an email if you're interested in something like this, so we can ensure that your application receives full consideration. 4 of the people, including someone from UC Denver over here, that co-authored some of the work that I talked about here today, they came to Argonne effectively as summer students. And then we also have a rich postdoc program, despite the fact that we don't have year-round PhD students everywhere, like at a great place like this. We have many postdocs. Okay, so we have in a group of something like 20 researchers, we expect to have on the order of 20 or 25 postdocs. And so there's an excellent culture for postdocs. You're finding future collaborators, future people to write research proposals with you, co-authors, so on and so forth. So as I told some people at lunch, the national labs are really, it's a sweet spot for postdocs at the national labs. You keep industry open and academia open. So I recommend that. And otherwise, I'll thank you again. It's a very pleasure to be back here in Colorado. Thanks.
Time for a few questions for Stefan.
Your favorite bases that you use in your local fitting lab?
Yeah,
so
this is so typically the first thing that we do in a code is start with the monomials. Okay, for conditioning reasons, often people use Lagrange because that brings you much closer to actually what the bounds look like. My personal favorite is to use something like radial basis functions. And part of the reason I do this is the ones that you add a linear tail for, you can at least get the first order information and still get nonlinear information over here at these scattered sites. The sub-problems that we solve tend to be a little bit more involved, as you might imagine, than for the quadratics. But that's usually trivial relative to the simulation space. Yeah,
So if you do the naive approach and you're given n+1 points, you can always find the fitting polynomial degree n, right?
Assuming that those points are affinely independent. So yes. Okay,
but that becomes very oscillatory if you have a large number of points. So do you ever use this in then a small number of dimensions, or it's completely out of it?
So I will tell you that in practical situations, we're dealing with smaller n cases where we don't go fewer than n+1 particular points. Is that your question?
But what is n then in your case? Is it still a large number? Or what?
No, so n is on the order of 6 to 30.
So you can still use it.
So you can still. But you have to be a little more clever with these models, I think, as you move on. And part of the observation, of course, is the linear algebra expense starts to grow with the dimensions, of course. Excellent question.
Alexander?
Can you give us some notion of the size of the problems that you're solving? Like, you sort of had some pictures of applications you might be working on, or the graph you have with stuff, jumping off down, depending on how much you were using. I mean, so what size of problems are you in terms of number of variables?
So let's go see if I was honest and go put some numbers. Okay, good. So for this number in very small font that you can't read from back there, it says n equals 15. So 15 decision variables and 11 constraints. So I would say that's a typical problem that walks in. The typical problem that someone walks in the door with is usually on the order of 3 variables. And there's a very specific reason for that. They walk in with 3 because 2 they do by hand. 2 they do sampling and plotting. Right? 3 they have a problem doing that immediately. Anything more than 3, they went and got it to some particle swarm optimization package, and it didn't do anything because it's just too expensive for their evaluations. So everyone walks in the door with 3 variables, and then as part of a dialogue, it's usually involved with modeling, then you say, actually, you have these other parameters. So once you can solve the 3-parameter problem, they say, now we can finally free up these other complex constants, and then when you free those up, then it's an ongoing process. But let's say on the order of, again, the typical problem between 3 dimensions and 30 dimensions is where we go. We've solved problems that are 300 dimensions, but those are very atypical, I'd say.
Yeah.
So in terms of detangling the objective and the constraints, let's say you have a single black box model that is evaluating the constraint and the objective with the same code. Is it still helpful to pull those apart, or is it better to go back to kind of avoiding that?
It's absolutely helpful to pull those apart. Yeah. So effectively what you're saying is you run the same code and it produces a constraint violation and the objective function value. Yes. Yeah. You should definitely be passing the constraints, the vector of constraints, and then the objective functions separately to a solver. The problem is you don't have a solver that does that. And so that's where my community has failed in making it easy to use solver for these particular applications. What that means is you have to send me an email, send Steve an email, send Peter Graff an email, people working in this area, and we'll write a solver for you. But please engage us until we come up with some better package. The real reason is that we're mathematicians at heart, and we know that there's not one solution for all these things. So it's very it's a slippery slope in black box optimization to say, here's a method that'll solve all your problems. Every problem's a little bit different, so we sort of, whatever. We revel in the dialogue with that case person. So send me an email, please.
So that's a great segue to my next question is, let's say I show up at your door with a black box, and I put it on your doorstep and I run away, and it just leaves, I have a card that says minimize me. What's the first thing you do with a black box?
I go looking for a make file and a better build.
Yeah?
Yeah. Yeah, so
what if I leave the box there and ring the doorbell and then stand there and say, I would like you to minimize my black box, but I'm willing to answer any questions you have about it?
Yeah, so my first answer is really serious. It's a challenge sort of to do that divide between application and optimization. The first thing that we would do is we would try to find out local, global, stochastic, deterministic, I don't know what the dimension is.
You have a checkbox.
And then we would do the thing, we would do some sort of linear and space filling design. We would use that design to give us some information about potentially how the function is coarsely changing over the space, something you know well. And then the benefit is that we could use that information to build our first set of models. And then start going optimization for local optimization. That's the way to go. So that's the answer.
Yeah.
The other thing I'll say is people care a lot about local versus global optimization. I'm a strong advocate for doing global optimization via local optimization. So doing something that at the end of the day you get a list of good local solutions rather than just doing some more stochastic sampling search through this whole space in an attempt to get an approximate global solution. Okay, so I think there's benefit from having distinct, disjoint, high quality local solutions. Local meaning that small perturbations are not going to lead to further decreases over here as a means of approximately solving a global optimization problem. And I think that's a more scalable process than a lot of the global optimization methods are actually.
Great. So let's thank Stefan one more time. I just want to have an announcement real quick. for. There we go. We will have our next colloquium 2 weeks from now on October 14th, and we'll be featuring Erica Graham from Bryn Mawr. And so please come back on October 14th. One last announcement. We will be sticking around for the next hour. If you have more technical questions, we're happy to have a more technical discussion. And if you want to join us at Trailhead Tap Room around 5:15, then please come down and meet us for a beer and dinner afterwards. So thanks for coming to Colloquium. See you next 2 weeks from now.
Thank you.
Yeah, good job.